All right. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, Lord, I thank you for the students. Just ask you to bless this time we have together. Lord, in your name I pray. Amen. So, I told you guys that I would try to talk about conic sections here, actually, which is kind of an untraditional topic for abstract algebra 2, but I thought it might be fun since we have a little bit of time left, and I don't really want to get started into something too super serious. So I thought this would be a good way for us to end things here. Let's see here. There we go. I've got, I have 5, so I have the ones that matter, but I also want to give Liam 3 chances, just to. I'm gonna leave it open. I'm gonna give you a chance. We'll see if you get it. So.
Oh yeah, let's go!
Wow.
Your boy is here today.
It was too easy. Yeah,
Actually, it was the second one I tried. Actually, I thought maybe you should put the whole thing upside down.
Uh-huh.
Upside down.
So I tried 9606 first. And it didn't work, so then I put 690.
Well, we'll have to up our game next time. Yeah. We'll increase the difficulty next time. We'll make sure you don't get it next time. Let's see here. All right. So, come on. Seriously?
Oh, so did you literally just into the
Well, that was way off.
That's hilarious. That is absolutely hilarious.
So conic sections, right? What is a conic section? Why is it called a conic section? So essentially, the naming comes from the fact that if you look at a double cone, right, you can imagine slicing that various different ways, right? And so let's see here. Some different ways you could slice it. One way, kind of a boring way you could slice it, would just be to take the horizontal plane, and then it would intersect just at the vertex of the, just at the vertex of the cone. So a point is possible, right? You could have a point. If you took the vertical plane like this, right, then it would actually intersect along these lines. So we could have lines, right? That's another thing that's formed by the intersection of a cone and a plane. I need a new cone at this point. You could also think about slicing the cone something like, like this, right? And then it would intersect along something like this, right? So you could have an ellipse. And of course, as a special case, you get a circle, right? If you did a horizontal slice like that. But then the other thing you could do would be something like, let's see here. You could also, well, I can't draw these worth anything, but if you look at it, you can also obtain a hyperbola or even a parabola if you slice it more like, let's see here. If you were to slice something like this, right, you get like something up here and something down there. So you get a pair of, you get like a hyperbola like that. Or if you had a slice that was such that it just hits one of the cones, you know, something like that. I'm still not doing justice to it. It would give you something that would be like a parabola. It's a horrible picture. Anyway, these are the conic sections that are possible. And the reason they're called conic sections is it's like you're cutting a cone, right? Section means cut. Now, as a point of order, these two are sometimes called degenerate conics, but these are the, I don't know what you call it, non-degenerate, I suppose. So I think if a person's talking about a conic section, a lot of times they're talking about a non-degenerate conic section, although technically speaking, points and lines are special cases. Now, if you wanted to prove something about a conic section from this perspective, it's really quite horrible, right? Because you got to think about how can you visualize cutting cones into particular slices and proving properties about cones which are cut in particular ways. It seems quite horrible to me to prove anything about conic sections from this viewpoint. So I much, much prefer the following definition for conic section. And here's the other definition, algebraic, let's say, which is that a conic section is the solution set of an equation of the form ax squared plus bxy plus cy squared plus dx plus ey plus f equal to 0. And then we say solutions which are points or lines are degenerate. Degenerate conics, right? Now this is a definition that we can sink our teeth into, right? Like, I mean, this is a definition that is nice to work with because it's got an equation and we can bring to bear the tools of algebra on this definition, right? But it does kind of beg the question, how are these equivalent, right? So to show these are equivalent, I suppose what we should do is show that, well, solution sets of that include what? Lines, points, ellipses, hyperbolas, and parabolas, and nothing more, right? The and nothing more is the kind of hard part. Let's get the point done with. So, to get the point, simple enough, right? Take f equals to 0, any a, b, c, d you like, whatever, right? Then 0, 0 solves it, right? We call this star. So, yay, we got a point. How can we get lines? To get lines, let's just look at the case a equals b equals c equals 0. Then you've got dx plus ey plus f equals to 0. And this is the equation of a line. Right? It's the big boy, big girl definition of a line. Right? I mean, you're no y equals mx plus b. Fine, if e is non-zero, you can solve for y. And if e is 0, then it's, okay, fine. I do need that, you got me. We do need that at least one of d or e is non-zero. Right? I mean, there are two more stupid cases that are possible for the solution set to this equation, which is what? If all of the coefficients are 0, it's the 0 equation, which is vacuously true for the whole plane, right? And on the other hand, if all of the coefficients are 0 except for f, and f is non-zero, the solution set is empty. Also possible, right? So I should say that, you know, we kind of want to ignore those in this discussion, right? All right. So we got point, we got line. Then what do we do? B and C 0. What would that get me? I mean, I'm not against that. We could, I mean, that's a choice we could make. We could say, we could put B equal to 0. We could put C equals to 0. And, oh yeah, very good. And then I put E equal to 1 just to keep our life simple, right? Or E equal minus 1. Then we'd have Y equals what? AX squared plus DX plus F, right? And you guys know that that's a parabola, right? It's a parabola that opens up or down, depending on whether it's positive or negative, right? And just as well, we could play the game A equals 0, A and B both 0, and we could leave the C non-zero, and we could get a parabola which opens left or right just the same, right? Pretty easily we could do that. How do we get an ellipse from this equation? D and E equals 0. So that would give us something like AX squared plus CY squared equals to minus F, right? And then, so what's our usual, how do we like to write ellipses typically? What's our sort of standard form? X squared over minus F over A, right? Plus Y squared over minus F over C, right? Equals to 1. I mean, if I did that, that would sort of be in standard form. I would probably, I mean, as a point of usual order, I would say minus F over A. I would hope, minus F over big A, I would set equal to little a squared, you know? And minus F over C equal to little b squared. And then I would have x squared over a squared plus y squared over b squared equal to 1, which for me would be an ellipse in standard form, where I could identify the vertices as like a comma 0, minus a comma 0, 0 comma b, 0 comma minus b. Those would be the vertices of the ellipse, right? And if we play the same game, but we make, you know, for that to work, I need f as negative, right? I'm assuming f is negative and that a and c are positive, for example. But to get a hyperbola, I would do the same thing, except, you know, suppose the signs were a little bit different. Then I'd have the x squared minus y squared would equal to 1, right? With appropriate coefficients downstairs. That would give me a hyperbola, right? So I think I've at least, I hope I've convinced you that it's definitely got all the different cases in it, at least that much, right? Let's try to give some sort of indication for why that's all that there is here. What strategy should we use to convince ourselves that, you know, that's all that there is? I think it's helpful to engage in a program of b equals to 0 to start with. So we're going to look at the context b equals to 0. Then we're facing what? Ax squared plus dx plus cy squared plus ey equals to, say, minus f. Right? So what can I do on this thing? I'm trying to show you that we can rewrite the equation as a ellipse or hyperbola. I think. Well, you know, if some of these are 0, it could drop back to a parabola again, right? But you know, what I'd have here is I'd have a times what? Times x minus d over 2a squared, right? Plus c times y minus e over 2c squared, right? Completing the square in x and completing the square in y equals to something horrible. A d squared over 4, oh, I don't even know, 4, goodness gracious, 4a squared, I guess, plus c e squared over 4c squared, all minus f. Great. No? Don't see it? Don't care. Okay, see. I'm quite certain you're capable of seeing this. Like, I'm not really worried about that. But I mean, you might be wondering, why are we doing what we're doing? Again, I'm trying to give a convincing argument that no matter what your choice of A, B, C, or D, or F, any choice of constants here, we can always bring it back into the form of a, you know, one of these guys. So, all right, now, so there's different cases, right? If A and C are both positive, and this quantity ends up being negative, the answer is that there is nothing. The solution set's just empty. If you have the sum of positive things is equal to negative, there's no solution. However, if both of these are positive, A and C are both positive, and this quantity also happens to be positive, then you're looking at a ellipse. Because it's a sum of squares equals to a positive constant, that's an ellipse. If your pattern is like plus, minus, plus, if these two terms differ in sign, it's a hyperbola. All right. So okay. Well, great. What about B then? What if B is non-zero? Then what should we do? I would argue pretty much the same thing. You know, what if B is not equal to 0? What do we do then? Well, I say what we do is we just do. I think we can just do the same thing, right? X minus d over 2a squared plus b parentheses x minus d over 2a times y minus e over 2c, yeah? Plus c times y minus e over 2c squared equals to ad squared over 4a squared. You might wonder why I haven't canceled out the a. There's no particularly good reason for it. It's just what I didn't do. 4c squared minus f. And then now what? What have I done? Oh, curses. I don't know. Oh, phooey. I'm not sure I can just do it like that. I'm trying to rewrite it. I'm trying to rewrite the quadratic, the conic section so it's just in terms of shifted variables at second order. I'm trying to absorb all of the linear terms into the second order terms is what my goal is. And because then I can write it as a quadratic form, and then I can tell you things very concretely about that. That's what I'm trying to do at the moment. I mean, so this achieves that goal, but I'm not sure it's honest, not yet anyway. certainly what I've done just by doing this is I've added b times minus d over 2a times that, right? So I have to add b d over 2a, right? E over 2c, because I added it to the other side, didn't I? So, but what's the trouble? I didn't just add that, did I? What else did I add? By rewriting that term like that, I've also added linear terms, right? So this has also b d over 2a. I have to add that, right? And I have to add bx e over 2c to be fair on that side, right? At which point I've spoiled the completing of the square. See, I can't complete the square for the a and the c term in isolation and then come back and address the middle term. I have to somehow complete the square on all of it. It's intertwangled, is my point. To use a technical term which doesn't exist. Curses, you know. So in summary on this calculation, oh well. So maybe you guys have a strategy if I'm going to try to rewrite ax squared plus bxy plus cy squared, you know, plus dx plus ey plus f equal to 0. I want to rewrite this as, you know, some constant. I don't even know. I mean, probably a. I'm guessing you can put an a here. You know, something like x bar squared. Let's say a bar x bar squared plus c bar y bar squared equals to f bar. I want to find a way to take my given set of constants and find a new set of constants, a bar, c bar, and f bar, where x bar is something like, you know, it's most likely something like x plus alpha, and y bar is something like y plus beta. If I had to guess, you can get away with that much. That's what I want. Having stated that, I bet we can work it out just by multiplying out what we're trying to do and looking at what we have and like solving systems of equations, equating coefficients of like powers of x's and y's and such. Do you think we can do it? I bet we can do it. Let's try. So we'd have a bar. What's x bar squared? It's x squared plus 2x alpha plus alpha squared, right? Plus c bar times y squared plus 2y beta plus beta squared, excuse me, equals to f bar, right? But there's something else that I haven't. Let me rewrite it this way: minus f bar equals to 0, because I also want the thing I'm not connecting enough yet is I want this to literally be that. So I have another relation. I have that this is equal to ax squared plus bxy plus cy squared plus dx plus ey plus f. I was taking a bar and c bar as arbitrary just to like point out that we should allow ourselves that flexibility, but I think you can see here by looking at the coefficients of x squared and y squared on both sides that the first thing is a bar equals to a and c bar is equal to c. So we want that, right? So what does that tell us? What are we stuck with? We're then stuck with 2 alpha a here, right? That's my x term. What's over here? Oh, Dang it. I forgot. Curses. B bar, X bar, Y bar. I can't neglect. That's the whole point here. I'm sorry. I need the cross term. We can't avoid that, all right? It's there. Algebra alone, this kind of algebra will not eliminate that. We need a deeper algebra to eliminate that. Yeah? So I should really put that up here. What does that give me? That, right? That does not interfere with my A bar equals to A or C bar equals to C reasoning, right? Those are still fine. But when I look at X, what's coming into play with X? When we look at coefficients of X, we pick up something over here, right? We get a B bar, beta, yeah? This times beta, there's an X here, right? And there's also an X here, plus what? Plus 2a alpha, right? And what is it equal to? D. How about the y terms? For y, we've got b bar alpha from this term, nothing from here, plus 2c beta equal to what? E. Now, alpha and beta are unknown. We're trying to find alpha and beta, right? So if you, so we should think of A, B, C, D, E, F as given, all right? And we should think of alpha and beta as unknown. Unfortunately, B bar is also unknown. So that's a bit of a drag, because I was almost hopeful that this was two equations and two unknowns, but the presence of this B bar spoils my party, does it not? So, gah. Curses upon you, B bar. All right, what else do we have? Oh, XY. Maybe XY will solve the mystery of B bar. So, not to be confused with Babar, who's a lovely fictional elephant. Let's see here. B bar, let's see here, X. Oh, just B bar. B bar is XY. No, B bar is equal to B. What do you know? Cool. All right, so actually, I retract my pessimism. This can be rewritten as 2a, right? B, B, 2c, alpha beta, dE. So if the determinant, the determinants matrix is what? 4ac, whoa. If 4ac minus b squared is not equal to 0, that's kind of funny. That pattern is coincidental to this argument. But it cracks me up. Then we can solve for this, right? Then alpha beta is equal to what? 1 over 4ac minus b squared. Flip the diagonals. Minus is on the off diagonal. I'm doing matrix multiplication by 2 inverse. So there's the alpha and beta that you want. And all that's left to do is what? I mean, that says that we can choose alpha and beta such that this is equal to that. I believe. Have I equated all coefficients? I equated, This was with x squared, right? This was with the y squared coefficient. There's the x squared coefficient, there's the y squared coefficient, there's the x coefficient, the y coefficient, the xy coefficient. What other coefficient is there to equate here? Looking at a quadratic polynomial in two variables. There's also the constant coefficient, right? What does the constant coefficient say? Constant coefficient gives us that b, alpha beta, plus a alpha squared plus c beta squared minus f bar equals to f. But again, given the condition that 4ac minus b squared is not equal to 0, it's straightforward to find f bar, and so we can rewrite the equation in this way. What about the case that 4ac minus b squared is equal to 0? What would that say? I don't know, I guess I'd have to get into that, but my suspicion is that that is the parabola case. That would be kind of what I would expect, is that's the parabola case. Because if that's not equal to 0, then we've rewritten the equation. Let me just point out to you. So if, let me summarize what we've shown, is if b squared minus 4ac is not equal to 0, then what we've just done is shown that the equation can be rewritten in the form a times x minus alpha squared plus b times x minus alpha times y minus beta plus c times y minus beta squared equals to some constant, I'll call it f bar. Right? But here's the thing. This, right, is nothing more than a quadratic form. So what we're really looking at is something of the form, let's say, well, it's a quadratic form in x minus alpha comma y minus beta equals to f bar. And what does a quadratic form look like? It has a formula, right? If I if I call this whole thing, let's say v, just for the sake of brevity, I can rewrite this formula as v, some matrix, well, v transpose, some matrix v again, right? And I can choose the matrix M to be symmetric, all right? So to be more specific, I mean, you guys don't look entirely convinced. Let me be brutally explicit about what I'm saying. What's the matrix? I'll do the easy part. A, C, B and D would almost be right. But we need to divide by 2. Because when you multiply it out, it gets you 2 copies of those, and you want it just to be B. So this is a real symmetric matrix. So the real spectral theorem says that that can be diagonalized orthonormally, and that the eigenvalues are real. So what that means is that you can rewrite this as, since I haven't used anything else, I'll use, say, lambda 1. Let's say y bar 1 squared plus lambda 2 y bar 2 squared, right? Where y bar 1 and y bar 2 are rotated coordinates with respect to your original x minus alpha and y minus beta coordinates. So what does that mean? Well, if you just think about setting that equal to the constant f bar, it's easy to understand how different, if we think about this equation equal to f bar, what are possible cases there? If lambda 1 and lambda 2 are both positive, it's an ellipse. If lambda 1 is positive and lambda 2 is negative, it's a hyperbola, or vice versa. If lambda 1 and lambda 2 are both negative, but f is positive, there's no solution, you know? If one of them's 0 and the other one's non-zero, it's a pair of lines, right? But the lines are rotated because it's a rotated coordinate system. So I think that should be a convincing proof to you that given the condition for AC minus B squared is not equal to 0, we can rotate coordinates and turn it into one of our beloved conic sections. Again, I'm operating off the assumption that we already have proved that, you know, we are aware, we are cognizant of the fundamental, these we use in calculus, right? X squared over A squared plus Y squared over B squared equals to 1, right? Or X squared over A squared minus Y squared over B squared equals to plus or minus 1, right? Ellipse, hyperbola. So I keep falling back on that as like a general backdrop to argue with you that different choices of the lambda will give me ellipses or hyperbolas. I'm assuming that we already know that to make that argument, right? I do wonder if I set that equal to 0, what does that mean for this equation? I actually don't want to get into that today. I'll try to look at it on my own and we'll talk about it next time, okay? To fill in that gap. What I want to talk about in the remaining time is the other definition of these conic sections. What's the other definition of ellipse? I'll try to make a copy for you guys next time of Anton's calculus. He actually has explicit formulas that you could tell like high schoolers or whatever to show them how to rotate coordinates, to put it into the form like I just did without linear algebra. He has it all set out at a level that anybody can understand who's interested in the discussion. You don't need linear algebra to do this. It's just to understand what you're doing. You need linear algebra to rotate the coordinates and so forth. In the same sense, you don't need the real spectral theorem, the proof of the real spectral theorem to use it either, do you? I mean, we could use it without understanding it, I suppose. But the other definition of the ellipse is what? How's it go? I have what? A pair of points. They're called focal points. And then what? No directrix here, but pair of focal points. Right? And without loss of generality, let's put them on the x-axis. All right? And we'll put them symmetric about the origin, just because we can. Given a pair of focal points, an ellipse is defined to be what? The set of points for which the sum of the distance from the given point to the focal points is held fixed as some constant, right? I'm not saying that very well, but given a pair of focal points, the ellipse is collection of all xy such that the distance from xy to focal point 1 plus the distance from xy to focal point 2 is held constant. I have a better here. I typed it out when I was in here, right? Here's a more erudite wording. Ellipse is defined as the collection of points for which the sum of the distance from the focal points is a fixed constant. All right. Now, this picture in the middle, I should have drawn elsewhere because I don't really want to continue the picture there because now it's clumsy. But if we are going to agree that the focal points are on the x-axis, then we can find a specific formula for this ellipse, right? Let's do that. So again, my focal points. I'm assuming that C is positive, right? So, let's just picture it. Suppose this is a point on the ellipse, right? So that means that this distance plus that distance is the constant distance, right? So, let's see here. Well, anyway, I'm not going to... I have an animation that I'll show you to visualize that better, but I mean, that's what happens, but let's actually work it out. So this is, say, D1. This is D2. And we're saying that D1 plus D2 is equal to some constant, right? What is that constant? Well, let's label this point as a comma 0. I mean, it's got to have some label, all right? And well, what happens with D1 plus? If you think about taking this, this point, right? And think about when it's here, that's D1 plus D2, right? But what else is it? If we think about that point. If we think about that one, how far are we? What's D1? It's 2C, yeah?
No, it's just C plus A.
This is C plus A? That makes sense because 0 is in here, right? So what Liam is doing is that good. Wow. Sadness. Such sadness. Yeah. That's A, right? So C plus A is D1. And what's D2? A minus C, right? That distance would be A minus C. And so, what's the constant? The C's be canceling, we get 2A, right? But what is D1? So what we're looking at is the solution set of the square root of x plus c, quantity squared, plus y squared, plus the square root of x minus c, quantity squared, plus y squared, equals to 2a. That is the literal geometric implication of the sentence which I've given here to define ellipses, this collection of points, the sum of the distances. So there's the sum of the distances equal to a constant. That constant has to be 2a for this particular setup of the ellipse, right? And then you're like, okay, that's great, but how on earth does that give you the equation x squared over a squared plus y squared over b squared equals to 1? Is it obvious that gives you x squared over a squared plus y squared over b squared equals to 1? It is not obvious. But what you do, square it. Well, isolate your radical. Square both sides, what do we get? One of them's plus, one of them's minus.
Oh, I mean when you use the whole square root of
Oh, yes, yes, yes. Thank you, thank you, thank you. And you notice that so this gives us an x squared minus 2xc plus c squared, right? It's like the x squareds are canceling, right? And the y squareds cancel. X squared and y squared are gone. And what do we have? You're like, we have 0 class time. Nice try. Let's see here. 4xc. Oh, the c squareds cancel too, don't they? Right? So we get, I get 4xc over there, and minus 4a squared, yeah? You guys tell me if I'm wrong. Good. And then square both sides. And so we get what? Maybe, I don't know, fine. I should rewrite this. This is 16c times x, 16c squared times x minus a squared over c, I think. Eh? So then what? Oh, well, anyway, I am actually out of time. I'm sorry. I have worked this out. It works out. Let's see here.
Wait, what was the end result?
Oh, okay. Well, let me stop. Let me stop at the last step that I trust, which was that one. I will show you guys the details next time, actually, but. Come on, where'd you go? So it does work out to x squared over a squared plus y squared over b squared equals to 1. But the question is, what's b? Right? The answer is that c is the square root of a squared minus b squared. You're like, that's not really telling me what b is. Fair enough. Let's see here. So that makes b equal to what? Well, b squared is equal to a squared plus c squared. That much I can tell you. And I usually make b positive. So you can try working it out for yourself. You should be able to get that. But I will try to actually work it out carefully. I'll try to spend about like 10 minutes of class going through this. But there's at least 3 different competing ideas for what is an ellipse or a hyperbola, right? Conic section directly, solution set to an equation like that, or the thing we were probably taught first, which is the sum of the distances being fixed constant, right? But how many of you have actually ever seen the algebra done to show you that this reduces to that? It's not that hard. It's just eliminating the radical twice and being careful. But it is something that takes about, like, it took me about 20 minutes of careful algebra the first time because I made a mistake and so forth. Dr. Sprano has a PowerPoint that I have, I might show you, where he doesn't put this in at the start. He just leaves the constant as like a variable d, and he does all this algebra with that constant being variable, and only at the very end does he figure out that the constant is supposed to be 2a. It makes the algebra much worse. So, but anyway. All right, I shut up. Thanks, guys. I should have your test for you by Monday.